In today's video, we are going to discuss about the case of bouncing ball and the phenomenon that comes up is the problem that is associated with the bounces, the infinite number of bounces that we may consider, and we will also consider a near realistic case where we are taking the loss of energy as opposed to the previous cases in the junior level when we considered the energy remaining intact. But let's take up this case where we are taking the ball. This is a solid surface, and let's say we have a ball which was projected upward from the level 0, and we take it as z is equal to 0, and it takes up or goes up to a maximum height, let us say that is h, and it comes back. Well, it as it strikes the ground, it loses a portion of its energy, and we'll name the fraction, of course. But the loss in energy causes the next bounce or the next height to be lower than the previous one, and with each successive bounce it goes on losing energy, and we have such a condition, and it may continue for many more bounces, but we are not really concerned about all those. We will take a generalized situation for that, and what we can assume over here is that it is losing a fraction of its energy. Let's say it is losing a fraction, taking it as gamma of its energy. Now the energy that we are going to take up is obviously the motion. With the motion involved in the upward direction, the energy is completely considered to be kinetic. That is what is taking it in the upward direction. Now we started off with a velocity, say it is v, and it reached a maximum height h with the first projection, and then it came down. So that is the maximum height that was reached in the entire journey of the ball. Now if the velocity at the beginning of the nth bounce is taken as a vn, so velocity of the ball at the beginning of the nth bounce is supposedly taken as Vn, and we wish to obtain a relation between the previous velocity from the previous bounce, which is Vn minus 1. We'll see how it is related to that. Now for that kind of an approach, first up we have to see what's the relation that is building up through each bounce. Now let's consider the very starting point where we are considering the very first bounce. Now as it travels from this point over here that I'm ticking right now, and it is projected up and it reaches the maximum height, and then it comes down over here, and in that case supposedly on losing the fraction of energy, which is gamma, which is provided over here, it now shoots up with a velocity, let us say v1, which is the velocity that it has after the first bounce, and likewise after the nth bounce it is having vn, or at the beginning of the nth bounce, that is. So in that case we wish to relate v1 with v, and then we may relate v2 with v1, and let's check the results, comparing the results if we can come up to some generalized form of it. Now the data we have is that it is losing gamma fraction of its energy. Now initially at this point, uh, it had an energy, I'm writing it over here, it had an energy for a mass m, it had the energy of half mv squared. Now, with that bouncing, the first bounce that it experienced, it lost gamma fraction of its energy, which means from the total energy, it lost a fraction gamma, which is gamma times of half mv squared. And now it has a velocity v1, so now it has the energy of half m times v1 squared. So which means if I were to consider the left and right hand side of it, so I have half mv squared as the common term, 1 minus gamma on the left hand side, and on the right hand side I have half of m v1 squared. The half and the m's can get cancelled out on each side, so we have v1 to be equal to the root over of 1 minus gamma times of v. That's more or less the case, pretty straightforward. And if you go on to compare the case of v2 with v1, you would also check, I would insist that you check it from yourself, from your side. So what you get is v2 also is equal to 1 minus gamma times of v1. Now if we were to take it right up to the very beginning of it, then what we would obtain, I am writing it over here, what we would obtain is that if we are comparing the case of v2 with v, that is the first velocity with which it was projected upward, then what we obtain is that v2 is equal to 1 minus gamma under root, and then for v1 we again have 1 minus gamma times of v, so 1 minus gamma times of v. And what that is going to give us is, this is 1 minus gamma, well, we can take it as a squared and the root over as divided by 2. I have a reason for that, why I'm writing it like that, because we have to generalize it. So v2 is simply 1 minus gamma 2 over 2, powered 2 over 2 times, and that multiplied to v. So if we wish to calculate Vn in terms of Vn minus 1, which is the velocity that was projected in the previous bounce, then Vn, so velocity of the ball at the beginning of the nth bounce in relation to the velocity in the previous bounce, that's going to be Vn minus 1. Then they will be related by the same case that we have been observing over here, that is Vn is equal to 1 minus gamma under root Vn minus 1. And if we were to take it right up to the very beginning, then we have Vn is equal to 1 minus gamma, we can take the root as 1 over 2, and then for the nth case we have n over 2 times of v. V, which is the velocity of projection right from the very beginning. So we have here two important cases, or two generalized forms of the velocities and the relation between them. Now if we were to consider the time taken, now we are taking the time as t, the initial time as t, and then we can take it as t1, t2 as we did it for the velocity. Now the time taken for the first bounce, that is the motion right from the very beginning over here till it came down to this point, so between that it has climbed up the ascent followed by the descent, and we know from the case of free fall under gravity that with the vertical motion that we considered in the motion in a straight line case in kinematics, we know from that it is going to be t, which is equal to 2 times of v over g. That is the case of t, that is the very first time when the ball bounced back to the ground. that is at z is equal to 0 from the height h. Now if we were to consider the time t1 similarly, it will be related to v1, and with v1 being the velocity of projection in the next case, we will have t1, that is the time from here up until here. It will be 2v1 over g. Now if we were to relate those two times, then what we get is simply t1 over t would give me 2v1 over g, then then at the denominator we have 2v over g. The 2's cancel out, the g's cancel out. We know that v1 over v is going to give us 1 minus gamma under root, which we have learnt over here at the top right corner in that box. So we need to know the t, the initial time, from the expressions that we have at hand. Now the maximum height that it has gone is h, and if we use the relation that s is equal to ut plus half at squared, then we have s as h and t as this is the time that we are going to take as the half of the total time. So u is going to be v, and t is going to be, we can take it as t naught, that is the time it takes to reach the topmost point, because h is the distance it travels from z is equal to 0 to z is equal to h at the topmost point. So this is z is equal to h at the top. So h is equal to ut plus, because we have the acceleration to be acting in the opposite direction, that is in the downward direction, so half g t naught squared, and from that what we get is h is equal to, we could have used another easier form, but we wouldn't have obtained a t in that case. So with relation to h we'll have to use this. Now v is equal to, as we know, now hang on a minute, we need not use this formula actually, because this is not at all required. We can straight away go like this, as the final velocity at the top is 0 squared minus v squared is equal to 2 times of minus g times of h, and so we have h in terms of v, or we can say v in terms of h, so v is equal to 2gh, and that is what we are going to use over here. That is, using that we can obtain t, which is equal to u minus v minus u is equal to a times of t, and because we have that in terms of h, so we can use 2gh over g is going to give us t. So t is simply equal to 2h over g under root. So we get the value of t1 as 1 minus gamma times of 2h over g. Now this is the value of t1. Well, if you remember, we took it as t naught because it's half of that now, so this will be 2 times of that, with the 2 getting in within that under root sign. So we have this value to be equal to 8h over g. Now if you look at the relation over here, so for the nth velocity with the previous one, we have 1 minus gamma under root, which is the case we obtained for t1 and t, which is the first time and the previous time. So now what we can do is we can relate the nth time with the very first time. So this is t1, and if we were to calculate tn and relate it with t, which is this one over here, then what we need to do is just take this form. It will take this form, that is 1 minus gamma n over 2 times of t. And what is the value of t? Well, the value of t is, as we found it over here, is 2 times of t naught, and t naught being equal to root over of 2h over g. So we have this as 1 minus gamma n over 2 to root over of 8h over g. So this is the value of the time with the nth bounce in consideration. Now, the total time for n number of bounces. So for n bounces, we are considering a separate case over here. For n bounces, from small n we jump over to the capital N, we'll have a Tn, and let's say we are extending that n over to infinity, which means we are trying to obtain now the total bounce. So this, for n bounces, we are calculating the total time for those n number of bounces, with n extending up to infinity. Now you may be pretty aware that it's not going to bounce that many times, that is, infinity is a very large number, but the number when counted can be taken to a very, very large value. So it is not exactly an undefined value. It can be defined and it has a value, but the value may be very large. You may have plenty of bounces before the ball may come to rest, and we wish to obtain the time, the total time that it will take for those infinite number of bounces. Infinite, as I repeat it, is not exactly the case of undefined, but a very huge number that we may consider in the context of the bouncing of the ball. So now comes the case of Taylor series, where we have used the expansion. We can use the expansion to obtain the expression. Now we have a case where we have in Taylor series that x raised to the power n, where n is going from 0 to infinity, is going to give us 1 over 1 minus x. And that is exactly the case that we are going to use for that value of n when it is extending up to infinity. And we have the value of Tn over here, and the power term that we have is n over 2. We can consider that root again, and we just keep the n for that. So what we get over here is Tn now becomes equal to the root over term for 8h over g. That remains as such. There's no problem with that. But what happens to the case of 1 minus gamma under root? Well, 1 minus gamma under root whole to the power n, when taken in that series and when considered in the context of the Taylor series expansion, we end up with this expression, that is 1 over 1 minus 1 minus gamma under root. So this is the expression that we wish to obtain, that is the total time that it will take for those n number of bounces. Now if we are to consider the case of another case where we are taking this fraction, that is the fraction of energy that it is losing, to be very, very small. So if we have gamma to be very small, that is, it is losing a very small amount of energy, so we can take this under root, that is 1 minus gamma raised to the power 1 over 2. That becomes well, let me use the next page for that. It won't be sufficient over here, so I would require you to hold on to that expression for now. So if we are getting this gamma to be very small, Then what we get is a t. Now n is taken to infinity, let's just do it like that, and we have 8h over g under root, and this term over here 1 minus gamma under root. Now I express it as raised to the power half. That is equal to 8h over g under root, and we expand this term binomially because we can afford to do that with the value of gamma being very small, and that is why the binomial expansion will lead to the lead to the omission of the higher order terms, and we can just restrict ourselves to the first two terms. And then we open the bracket over there, so 1 minus 1 goes to 0, and minus multiplies with that minus half of gamma, which becomes plus. So we have this value to be equal to, so t infinity now becomes 8h over g under root, and then we have 2 over gamma. That half in the denominator becomes the 2 in the numerator over here. So this is the expression for the total time after infinite number of bounces, with the case of the fractional loss in energy to be very small. Otherwise, you can always consider the previous equation right there in the denominator over here. So with this, we can consider a few cases that may be related to this. Let's try a simple case over here and see what we can do with that. Now, in context to the above conditions that we just studied, if the total distance traveled by the ball during infinitely many bounces, well, you can consider the forward direction, but here I would suggest that you consider the vertical motion only, because we may not have the ball to be bouncing in the forward direction because it is only concerned with bounces. So I suggest that we take this distance that it has asked for as the vertical motion only. So although the displacement will be 0 after uh, the end of the event, but the distance for sure is going to add up with every bounce. So after infinitely many bounces, which is in fact finite in this case, that may be denoted by s, the total distance that is, and we have the solution actually over here, that is s is equal to 2h over gamma. We need to prove that. Well, let's see if we can do that. So the distance that it travels within the first bounce is equal to, so let me try the solution for it. So s1 is going to be the total distance. Let us say it is 2 times of s0. Now s0 is equal to the height h. So we have the value of h for sure is equal to v square over 2g, and similarly we have s2 to be equal to 2 times of s1, which is equal to 2 times of 1 minus gamma times of v squared, because it is going to be 1 minus gamma under root for v, but certainly for its square it's going to be 1 minus gamma as normal, and we have that over 2g. So nth case we have 2 times of Sn minus 1, and that is equal to 2 times of 1 minus gamma v squared over 2g. I hope I'm going in the right direction. Now the total number of bounces, or the total distance that we may consider, is equal to the sum of all these bounces or all these distances, that is equal to right up to Sn. So we have 2 times of v square over 2g can go as the common term, and then obviously this is raised to the power n for sure, because we are considering for the nth case with relation to the first velocity over there. So 2 times of v squared over 2g, and again we are considering infinitely many bounces, so we have the liberty to take this summation from 0 to infinity, and what is left in the bracketed within the summation is 1 minus gamma raised to the power n. and obviously you know that v square over 2g, we need not really write that, but just to relate the gamma with it, I use that, so it is simply 2h now. And as for this one, we have the famous Taylor expansion, which is giving us the result for this summation, which is 1 minus 1 minus the term which is raised to the power n. In this case, it is 1 minus gamma. We open the brackets. Once the ones goes to 0, go to 0, and then we have plus gamma over there. So all that we have left is 2h over gamma, and that is going to be the total distance that we are going to get after, let's say, infinitely many bounces. So this is a case that I just brought in to your notice. There are many such cases that we may consider, and this Taylor expansion that we have been studying and using may come handy at many occasions, many such occasions. So that's it from this video. I hope to bring in another case, another interesting case, another interesting problem to your notice related to any mathematical condition that we may come up with, especially the Taylor series. I hope that I can bring another case. Till then, thank you for watching.